Hello everyone. So we have already discussed baseband modulation techniques. Now we are going to start another topic which is based on multi-carrier modulation. And under this multi-carrier modulation, we will study about orthogonal frequency division multiplexing, which is OFDM. And we will see that it is more efficient than baseband. So what are the VLC challenges if I want to use OFDM technology or multi-carrier modulation technique? So why to go for OFDM? Because baseband can give you a limited data rate, and if you want to have high data rate, then one has to use some advanced modulation techniques. And we already know that the LEDs, they have very limited bandwidth. The commercial LEDs, which are generally used for illumination, they have very limited bandwidth of the order of tens of megahertz. And in order to get high data rate, we need to have uh, advanced modulation techniques. So OFDM is one option. Uh, and the other issue is that there is multipath propagation. If, for example, inside the room, this is your transmitter, this is your receiver, although the room is very small, so you can have line of sight component, you can have non-line of sight component, you can have components after multiple reflections. So this results into some sort of delay spread, which limits your data rate. So because of this multipath propagation, there may be some compromise on the data rate. And also VLC, we cannot use OFDM directly because OFDM signal is generally complex and bipolar, whereas if you want to give signal to a LED, it has to be a real signal and it has to be a unipolar signal. So some changes have to be done in the conventional OFDM systems in order to make it compatible with optical wireless communication systems. So let us discuss first about the single carrier systems and what is the data rate we get in a single carrier system. So single carrier system, just to give you some more applications of OFDM, we normally standards promotes in OFDM in 4G systems and also in wireless local area networks, that is 802.11a or G or N. They also use OFDM. So OFDM is quite popular in 4G applications and in wireless local area networks. So let us now go back to our single carrier system. Suppose I have a single carrier system. And the bandwidth is say B, which is equal to W, which is W is one-sided bandwidth. So the symbol duration is T. And for a single carrier system, T is equal to 1 by B. So you transmit one symbol every t seconds. So transmission of one symbol every t seconds, which means the rate is 1 by t or B. So for a single carrier system, the transmission rate is B. Now let us do this now differently. Let us break the whole bandwidth into n equal parts and examine what happens. So if my total bandwidth is, this is the total bandwidth B, and I break into this is middle, so on and so forth. This is the last one. And let us, this is say n by 2 into bn, b by n. The spacing between two carriers, these are all carriers with different frequencies, FIs, and the spacing or the spacing between two carriers or subband is b by n. And the last is n by 2 into b by n, and this one will be minus. So totally there are n subcarriers. This is b by n. So there are n subbands. Each corresponds to some carrier Fi, and the bandwidth between two adjacent frequencies is b by n. So let us take some example. If b is say 256 kilohertz and there are n subcarriers or different n is equal to 64 frequencies, then b by n, the spacing will be, then bandwidth per subband, bandwidth per subband is 250, this is over 64, is 4 kilohertz. So this b by n is 4 kilohertz. And the frequencies, different frequencies which are there is Fi I into b by n. So these are the frequencies here. And the fundamental frequencies is F0 b by n. And so the T0 will be 1 by F0, that is n by b. All right. So now what I do, now there are Fi subcarriers and I is actually going from, I goes from the limits of IR n by 2 and minus n by 2 minus 1. So that is the limit of I. Now I transmit data, this is Xi is data, this is data. Use Fi as the subcarrier frequency and these are called as subcarriers. So Xi data is on Fi subcarrier. So SIT will be Xi into e raised by j 2 pi Fit. And I can write Fi as b by n. This is Fi is equal to I b by n, I b by n t. And similarly, all the data Xi where I changes from n by 2 to n total n subcarriers, the data is Xi plus 1, Xi minus 1 and so on and so forth. So the total data, the composite signal, the combined signal carrying different data on different subcarriers is given by ST summation over I SIT, which can be written as XIE j 2 pi I b by nt. This is the composite signal which is transmitted. And now let us assume that there is no noise. Assume no noise. Ultimately, we will consider noise. But right now, just to understand about OFDM concepts, assume there is no noise in the system. So whatever is transmitted is received. So YT is same as ST, which is given by xi e raised to j 2 pi I by n t, where xi is the data which is riding on ith subcarrier. And similarly for other subcarriers, and I goes the total number of n subcarriers, and the range of I is between n by 2 and minus n by 2 minus 1. So now let us try to do this operation. F0 is the fundamental frequency, and take yt and take some frequency subcarrier fl, which is actually lth time the fundamental frequency lf naught, and multiply yt by the conjugate of this e raised to j 2 pi flt. Let us see what this operation does. So I have taken the fundamental frequency f naught, and yt is the received signal, and I multiply this by the conjugate of ae j 2 pi flt, and yt has signal corresponding to lth subcarrier. So f0 is, as we know, is given by b by n, and t0 we had calculated. So f0, the fundamental frequency is b by n, and t0 is n by b. So this is the limit, and this is the composite signal yt, and this multiplied by the conjugate. So this minus sign has come, e raised to minus j 2 pi l b by n dt. Now this has become, I have taken this factor inside, so this has become xi e raised to j 2 pi I minus l f naught t. I have replaced b by n by f naught. So now this has various components, and there will be a component which is I is equal to L, and the other component in the summation will be actually I not equal to L. So let us separate these two components. I equal to L will give me this. This is I equal to L, and I not equal to L will give me this I not equal to L. Now if I calculate this integral, this is nothing but XL, because this will be n by b, and b by n will cancel, and I'll get XL. So this will give me XL plus this component, the circled one, is actually 0, because if you see this I minus L f naught is some multiple of fundamental frequency f naught. So basically, and I and L, they're all integers. So if you integrate over these different multiples of f naught, the integral will give you 0. So, and also it amounts to saying that all the frequencies which are where I is not equal to L, they are orthogonal to each other. So this integral will be 0 because of orthogonality. So what I get is actually XL plus naught. So this is what I have written. XL, the second integral is 0. XL is the data which is riding on the LS subcarrier. So, and this is possible because of this property where this is 0 if I is not equal to L. If I is equal to L, this is equal to n by b. So actually what we have done earlier, we have multiplied this by the conjugate. So basically I have done a coherent demodulation. That means I have taken a frequency FL and I have coherently demodulated the composite signal, and I am able to recover XL. Same thing I can do for other subcarriers, FI or F1, F2, F3 and up to Fn. So I can basically demodulate all the data which is there on those subcarriers by doing this simple demodulation, coherent demodulation. So in MCM, that is in the multi-carrier modulation, that is multi which I did just now, the integration time is actually T naught, which is 1 by F naught, and which is nothing but N by B. So there are N symbols. They use N subcarriers in period T naught. So if I find out the symbol rate in MCM, it will be N divided by N by B, which is actually T naught. So this gives you B. So the symbol rate is B here as well. So in the single carrier also we saw the symbol rate is B, and here also it is symbol rate B in B. So the only difference is in OFDM, this whole is N by B. Let us not call it OFDM, still it is MCM. And in single carrier, this was T. This is one symbol, single carrier, and this is 1 by N, or T is 1 by N. So this is the difference, but in both the cases the symbol rate is B. Now let us draw a diagram for this multi-carrier modulation. How does it look like? So this is your symbol. The first operation you do is you do the serial to parallel conversion, and then you get different outputs. That is the different data. Which, for example, this is serial data xi plus 1 and so on and so forth. When you do the single, on top you'll have xi plus 1 and so on and so forth. And after this you will have a bank of modulators where whatever data is there on the ith subcarrier, this is, let us write, this is ith data, and then we use bank of modulators. So there are different modulators, and each is modulating. Ith data is getting modulated by ith subscriber, lth data is getting modulated by lth subscriber, so on and so forth, and there are n subcarriers. The total number is n subcarriers, or these total number is n. So each modulator is modulating the corresponding data, and then we use some sort of summer here, and this is sum of all subcarriers, sum of all subcarrier data, and this goes to the channel. So this is a transmitter for a multi-carrier modulation technique. And then whatever data is received, let us write this I is between n by 2, and this is n by 2 minus 1 minus. So these, you require n modulators for each subcarrier. Now on the receiver, you're receiving say YT. Right now let us assume that there is no noise added in the channel. Then maybe you have some sort of repeater so that the attenuation which has happened in the channel is taken care of. And then you have this goes to a bank of demodulators. These are coherent demodulation, because we saw that by coherently demodulating we are able to recover the data. So this goes here, and then you get the information symbol after demodulation, information symbol on each subcarrier, which was there on the E subcarrier. So information symbols, and then once you have got all the information symbols, you have parallel to serial converter, and this is your recovered data. Recovered. So this was a required stream, or this we can call it input stream. This is a recovered stream. So this is how a typical block diagram of a transmitter and receiver of MCM. You have input stream, you divide into n parts, and each has data which goes to a bank of modulators, and after modulating it is summed. You sum them up, and it is transmitted over the channel. And the channel, then again you, from the combined signal, we have seen in earlier slide that by coherently demodulating you are able to recover the data. So this is a set of demodulators where you are able to recover the data or information symbols, and then you combine them, parallel to serial or some sort of mux, to recover the original stream. So let us see some example to understand some numbers. So suppose your B is 1.024 megahertz, and BC, which is a coherence bandwidth in a wireless channel, is of the order of say 250 kilohertz. I mean, I'm talking about right now wireless channel, not right now I have not introduced the optical part, because currently I am giving the fundamentals of OFDM. Once we understand the OFDM as it is used in RF, then we will try to map it to our VLC applications. But right now it is for as it is used in RF applications. So the coherence, this is the coherence bandwidth. So as we see here, B is much greater than BC. That means it's a frequency selective channel, because the coherence bandwidth is much less than the bandwidth of the channel. So it's a frequency selective channel. So in MCM, this was the case with single carrier, for example. In MCM, now you have divided the bandwidth into n parts, B by n. So B by n is now much smaller than BC. The channel becomes actually flat. So that's the advantage of having multi-carrier. The channel behaves like a flat channel, because the sub-channel bandwidth, if you see, B by n, is much less than BC, which you can calculate, divide by 64 depending on how many subcarriers you're using, or 256. It is much less than BC. Channel is flat. So in MCM, this problem is resolved, which was there in single carrier system. But the main problem is that one has to use so many modulators and demodulators. So the hardware becomes very complex. The hardware becomes very complex because it uses n modulators and demodulators. And if n is high, 256, then it becomes very, very complex. So that is the issue with the multi-carrier. Although the channel has become a flat channel because the bandwidth B by N, the subband bandwidth, is much less than the BC, and so you are able to recover your data signal. So how to solve this problem of hardware, complex hardware? How to get rid of this so many modulators and demodulators, which makes your circuit very complex. So let us try to understand this, and this was solved by two engineers, Weinstein and Ebert. So what they did that your ST signal has bandwidth B. Now, if I sample this system, this signal at Nyquist rate, sample at Nyquist rate, which is Ts given by 1 by B. That is the rate I sample at. So I get a UH sample which is at instant UTS. This is the UH sample at UTS. This is SIT. So the signal, the combined signal, if I sample at Nyquist rate, the bandwidth is B. So the Nyquist rate will be Ts is equal to 1 by B. I will get a series of samples. And let me call that as UTS, which is actually the UH sample at time instant UTS. And UTS is equal to U by B. So the ST or the combined signal, actually it is summation over all subcarriers xi, these are the data, e raised to power j 2 pi I b n by t. This is my SIT. Now I sample. So the sample UTS, call this as XU. This is the UH sample. I'll be denoting the sample with a lowercase. So this XU is the UH sample. So this will be I xi e raised to j 2 pi I b by n u by b. So this becomes I xi e raised to j 2 pi I u by n. So if you notice this carefully, this is actually IDFT. inverse digital Fourier transform. And xi are the coefficients. So I can recover this xi from this IDFT, from these samples. So this becomes very, very easy. I don't have to have bank of modulators and demodulators. Simply I recover the coefficients of the signal, and they are actually xi's. So this becomes little simpler now, and in OFDM this IDFT is actually IFFT, inverse fast Fourier transform. This is discrete, I'm sorry, inverse discrete Fourier transform. And in the OFDM context, it is inverse fast Fourier transform. So the problem of bank of modulators and demodulators is solved by simply taking IFFT or IDFT, and the coefficients are actually will give you the data symbols. So let us make the block diagram of the block diagram will get slightly modified, and maybe we can make the block diagram here. So this is your data stream, and then you do signals serial to parallel, and these are the symbols and -1 or the constellation points in the signal, and then you have the IFFT. This is endpoint IFFT. Still it is not complete OFDM, but we will see, we'll add some more thing to make it complete OFDM. So this is endpoint IFFT, and then you get these samples. So these small cases denoted as samples. This is x and -1. So these are the samples after sampling it using Nyquist rate. And then you have parallel to serial converter, and then a series of samples, which is x0, x1, so on and so forth up to x and -1. So this whole thing is a OFDM symbol. So actually that CPL is also added, that cyclic prefix. Right now I'm not adding it, but first I have to explain why CP is added. Then actually the whole signal, when you have the cyclic prefix and this whole symbol, that becomes a OFDM symbol. Now these samples, this is x0 to xn -1, they go to serial to parallel. So these are the samples, and then you do the reverse operation. In the transmitter you had done endpoint IFFT, now you will do endpoint FFT, and then you are able to recover the coefficients of IFFT. The coefficients are nothing but the data symbols. So this is x0, and this will be capital S xn -1, and then you have parallel to serial converter, and you get your data stream out. This is your data stream. This is input data stream. So by doing this IFFT FFT operation, we are able to get rid of the bank of modulators and demodulators. So it becomes quite simple.